So welcome back from Thanksgiving. We have just about 3 weeks before Christmas, so we have one last chapter we're going to cover for this semester. Technically 2 chapters, one last unit, I should say. Chapter 10, which is liquids, solids, and IMFs, which if you remember from Chem 1, stands for intermolecular forces. And then Chapter 11, over solutions. We're going to do that as all one unit. So before we get started in the notes, let's recall Coulombic attraction, because it's going to rear its head again in this unit. Of course, here's your formula. The numerator is the charges of the particles, and of course the bottom is the distance. If you remember from bonding, which y'all did very well on that test, the question was which is more important, the charge differences or the size differences. And usually it's the charge differences. There's always exceptions to that, but usually it is the charge differences that make a bigger difference in the Coulombic attraction. When we're talking about phase changes in this unit, and we're going to be discussing it, we're going to discuss the Coulombic interactions or the electrostatic forces being overcome. If it is going to be solid to liquid, liquid to gas, you're going to need to talk about those. Coulomb's law is also involved when discussing the dissolving process of ionic compounds. So let's talk about the difference between intramolecular bonding and intermolecular bonding. Intra means between the electrons. They're sharing the electrons. That means the nuclei are interacting with the electron clouds of a nearby atom. Intermolecular is basically the forces that are going to hold one molecule to each other or a group of ions to each other. It is the interaction between particles, atoms, molecules, or ions. There are going to be basically 3 types that we're going to discuss. When we are talking about condensed state of matter, we're talking about liquids and solids. And when we are talking about, this is important, when you are going to be discussing changes in state, you're going to be talking about intermolecular bonding, which are physical changes, not intra. This is a huge mistake that kids make on the AP exam every year. They will talk about things, well, the bond's not as strong between the atoms. And when we're talking about why something becomes a liquid or freezes to become a solid, we have to talk about the intermolecular forces, not the intra. Okay? So get that in your mind now. In this unit, we should not be talking about the strength of an ionic bond versus the strength of a covalent bond versus the strength of a metallic bond. We will be talking about the strength of the intramolecular forces, or IMFs for short. So the first type we're going to talk about is a dipole-dipole attraction, and that is when a molecule has a dipole moment. In other words, slightly positive, slightly negative side. There's an attraction for each other. Opposites attract. So polar molecules will have dipole-dipole interactions. All polar molecules have dipole-dipole interactions. And so here's kind of a visual here. You can see that the attractive force in red is the positives and negatives being attracted to each other. And of course the repulsion is the 2 positives or the 2 negatives. And they will orient themselves, the molecules themselves, will orient them to minimize those repulsions and maximize the attractions. So dipole-dipole attractions are only about as strong as a covalent as 1% of covalent ionics. So intermolecular forces are weaker than the intra. Okay, molecules orient themselves, we already said this, to minimize those repulsions and maximize the attractions. Here's 2 examples of things that have dipole attractions: HCl and H2S, which is hydrogen sulfide is what they usually call it. It's a very smelly gas. Hydrogen bonding, we should remember that from Chem 1, is an unusually strong dipole-dipole attraction. It is a type of dipole-dipole attractions involving hydrogen atoms which are covalently bonded to a very electronegative element and a small, it has to also be a small, very electronegative element. So that is where we've come in with no orange friends. Some people say hydrogen bonding is fun, F-O-N, but we came up with it actually years ago, one of my students did, of no orange friends: nitrogen, oxygen, and fluorine. And they're bonding, the hydrogen is bonding with the unshared electrons on those 3 things. Here is the mistake that a lot of kids make, is they see NOF present in a molecule, and they'll say, oh, it's got hydrogen bonding. But they neglect to see, does it also have a hydrogen? Not only does it have to have a hydrogen in the molecule, but the hydrogen has to be connected, has to be bonded to the nitrogen, oxygen, or fluorine. So keep that in mind. Just because you see an oxygen, especially in an organic molecule, you need to make sure that it's actually connected to the hydrogen. So here is a pictorial of hydrogen bonding in water, and you can see where the hydrogen is going to be attracted to the or the lone pair, on the oxygen. There are two reasons for the strength of hydrogen bonding. One is the small size of the hydrogen atom allows closeness to the other atoms, such as the nitrogen, oxygen, or fluorine, and of course greater polarity. Substances with hydrogen bonding have much higher boiling points than they should. Here are some examples of H2O. Ammonia has hydrogen bonding. Not only do they have a higher boiling point, they evaporate more slowly. Think about the difference between water and Germ-X. Germ-X is alcohol-based, and Germ-X evaporates very quickly off your hands, whereas water takes a while to evaporate. And that's another example of hydrogen bonding being a higher boiling point or a higher evaporation point. When we normally think of bonding occurring between two different molecules, very large molecules, such as proteins, have different parts of the same molecule, and they can form hydrogen bonds. And here example is your alpha helix, and there's forming hydrogen bonds to help hold that molecule and do that little double helix structure. So here's an important tip. When you're discussing hydrogen bonding in an essay, always make it very clear that it is the attraction between the adjacent molecules. Otherwise, it sounds if you believe that the covalent bond is the hydrogen and nitrogen, oxygen, or fluorine. We need to talk about adjacent. Make sure you say between adjacent molecules. Between adjacent molecules. Anytime you're discussing any kind of intermolecular forces, you should talk about between adjacent molecules. Do not make it unclear and make the reader think that you think it's between, say, the hydrogen and the chlorine itself. It's not between the hydrogen and chlorine. It's between the hydrogen of one molecule and the chlorine of an adjacent molecule would be a dipole-dipole force. Okay, so make sure you say between adjacent molecules. The London dispersion forces are the LDFs. They are the relatively weak forces that usually exist between noble gases and between nonpolar molecules. They are the only force that acts upon nonpolar. I can't say that today. They are the only force that acts upon nonpolar molecules and noble gases. However, and here's where kids get confused, they also exist in polar compounds, and they also exist in things that have hydrogen bonding. And in Chem 1, we say, oh, they're the weakest of the three forces, but in actuality, LDFs may be the most important force, especially in very large molecules. Especially in very large molecules. And the reason for that is London dispersion forces, if you remember, are occurring because of the momentary imbalance, or we call it a temporary or an induced dipole, which can induce that same on an adjacent molecule. And it's because of the electron imbalance. So why would you think that in larger molecules that the LDF is more important? And the reason for that is because larger molecules have a lot more electrons. So here are some visuals to kind of get you looking at that. So the more atoms that you have, or not the more atoms, the more electrons, the stronger that dipole becomes. And remember, it's basically that induced dipole or that temporary imbalance. It's there and it's gone, it's there and it's gone. But there's constantly these temporary dipoles or these instantaneous dipoles being induced, and so this is why you have London dispersion forces. And this is just kind of explaining that, so you can read through that. It's also in your notes. Again, I want to reiterate that polar molecules and even ions can cause an induced dipole. So kids tend to get confused, or they tend to think that LDFs only happen on nonpolar molecules. So I want to restate that just to make sure that you've got it, that LDFs occur in all of the molecules, okay? Polar, nonpolar alike. But they are the only ones that act upon nonpolar, okay? So don't think that they only happen on nonpolar. They happen on nonpolar. They're the only ones that happen on nonpolar, but they also happen on polar molecules, okay? This force is often very weak, and that's why the boiling points of gases, especially the noble gases, but the boiling point of the noble gases as you go down the group actually increases because you have more electrons. We call this more polarizable, or sometimes we say it has more polarizability when they have more electrons. So if you look at this graph of the noble gases, you can see that the boiling point increases significantly for radon as opposed to helium, which has very few electrons. Always when you're discussing London dispersion forces, always discuss the fact that they have more electrons, which means they are more polarizable. Never just say it's bigger, it has more mass, okay? That is not the reason that the boiling point goes up, just because it's bigger. It's because of the electrons, and the electrons are inducing more of these dipoles, which causes the force to be higher. So please, if it's not in your notes, write it down, highlight it, put a star by it. Always discuss number of electrons equals more polarizable. Never discuss size or mass on intermolecular forces. So if you're looking at group 4, the boiling point of covalent hydrides, which means it has hydrogen with it, increases with molar mass. That's because, again, more electrons. So in other groups, the first hydride has a higher boiling point because of hydrogen bonding. So if you look at group 16, water, H2O, is going to have a higher boiling point because of the hydrogen bonding. And here is an example of that. So if you look at all of those, you'll see that because of hydrogen bonding in group 6, group 7, just 16, 17, and group 15, they have a much higher boiling point. But if you go look at group 14, excuse me, they're saying 4A. I forget to refer to it that way. I just call it group 14. There's no hydrogen bonding in methane, and so you see that the boiling points are more in line for increasing as you get more electrons by having a higher thing that hydrogen is bonded with. When we talk about metallic bonding, we're talking about the reason that they stay together. Metallic elements have metal cations in that sea of mobile valence electrons. So they are going to be not really discussed as far as intermolecular forces because they're held together by that sea of mobile electrons. Ionic bonding, of course, is cations and anions, and that's usually metal and a nonmetal, and they are held together by that electrostatic or that Coulombic attraction. Covalent network bonding, this is when you have an extensive covalent bonding between atoms, and this results in giant molecules, and we'll discuss this a little bit further later in a little bit more detail. So group 4, this is group 14, they're referring to 4A, are often involved with covalent network bonding. You've got carbon, and of course carbon has several different forms. You can have carbon as graphite, you can have carbon as diamond, and you can have carbon as another one, a big, huge carbon-60, which is called Buckminster fullerene. I promise you, I did not make that word up. And then metallic, ionic, and covalent will be discussed a little bit later. Okay. The general trend in the strength of attraction is LDF, dipole-dipole, hydrogen bonding, then metallic bonding, and then ionic bonding, and the strongest is your covalent network solid. And while these are general trends, there are many exceptions. If given the data, use the data and use what you know that that particular substance is undergoing in terms of intermolecular attractions. Okay, IMFs. So here are your list. And again, I'm going to caution you on saying that LDF is the weakest. It is the weakest in terms of the attraction, but it can be more powerful than a dipole-dipole, for instance, if it's a very large molecule. Okay, so keep that in mind. Larger molecule, the LDFs become more important. Okay, so on this slide, we're going to determine the type of intermolecular force that each of the substance has. So here we go, hydrogen. Actually, I want you to pause the video and you try to determine it, and then we'll come back to it. Okay, here's what we came up with. Hopefully you got these same things. If in doubt, for instance, for the CO2, you want to draw out the Lewis structure, and so you can determine is that polar or nonpolar, because that would make a difference. So in this case, we didn't have anything that showed up with hydrogen bonding. So there we go. Let's keep moving on. And then on this slide, I want you to rank these substances from the lowest boiling point to the highest boiling point, and then I want you to justify your answers. So I'm going to pause the video again. You do as well. Okay, let's resume. So first thing I did here was I'm going to do the obvious, and I'm going to separate them by their states of matter, because obviously the gases are going to have a much lower boiling point than the solids. So within those, then I can make that a little bit easier and do each list. Well, water's by itself, so it's going to be somewhere in the middle. Okay, so I want to look at my gases first. I have NH3, which would have hydrogen bonding. I have F2, which is nonpolar, so it's only going to have LDFs. And then I have SO2, which is also a gas. And then it's going to have, it is a polar molecule, so if I draw it, it looks like this. And then, oops, my lone pairs, double bonded oxygens. So it would be a polar molecule, so it would have dipole-dipole. But it's also a large, much larger molecule than the other one, because it's got a lot more electrons. So it's also going to have fairly high LDFs. So I'm going to call it the highest of the gases. So I would rate this so far as I would say F2 would be the lowest, then NH3, and then SO2. Okay, because of the LDFs, having much more electrons, it's going to have much higher boiling point than the rest of those. And then comes water, because it's a liquid. And then I go over here, which let's just go ahead and say hydrogen bonding for water, but it's kind of got to be there because it's a liquid. And then we go over to the solids, and we have sodium chloride and we have germanium. And we know sodium chloride is an ionic compound. But if we look at germanium, it's in group 14. And earlier in the notes we said that, germanium is group 14, which is capable of covalent network bonding, which in fact it is. And so then that means it's going to have a higher boiling point. So then we would go with sodium chloride, and germanium. Okay? And just to give you an idea of the difference in boiling points, germanium is 2833 degrees Celsius. Way down here, fluorine is a negative 188. And that kind of gives you an idea what we're dealing with. Just so you know that sodium chloride is 1413, so it is quite a bit lower than germanium. Okay? So we are almost done, I promise. Got a few more, and then we're going to be done. Some of the behaviors of things are due to their intermolecular forces. For instance, surface tension, of course, is the resistance of a liquid to increase its surface areas. Liquids with very high intermolecular forces have high surface tensions. So, of course, water is one of those. That's why bugs can float on water. That's why things can float on top of water and not sink. And it's because of that high intermolecular forces equals high surface tension. Polar molecules will have more surface tension than nonpolar because they have higher intermolecular forces. Capillary action is another one. Again, high intermolecular force, high. Spontaneous, of course, just a second. Someone's knocking at the door. Sorry about that interruption. Capillary action, of course, is the spontaneous rising of a polar liquid in a narrow tube. That is why you can drink out of a straw. It's caused by two forces. They're cohesive and adhesive forces. Cohesive forces are the intermolecular forces among the liquid molecules and between the two molecules. And then adhesive is the forces between the liquid and their container. So the container must be made of a polar molecule such as glass. A concave meniscus, of course, forms because the water adhesive forces toward the glass are stronger than its cohesive forces. And a nonpolar liquid, such as liquid mercury, can produce a convex meniscus, and that's because its cohesive forces are stronger than its adhesive forces. Viscosity is one of the last things we'll discuss today, and that is the resistance of flow. Basically, viscosity means it's a very thick liquid, such as molasses, compared to, say, water. Liquids with very large intermolecular forces tend to be highly viscous, and this is an example of glycerol. And it has, again, just like the surface tension and such, high intermolecular forces means it has a high viscosity. More complex molecules are more viscous because they tend to get tangled up with each other. And then that is where we're stopping today.